Okay, shall we begin? Just saw someone attending the class, so let him sit down as well. Okay, so hello, ladies and gentlemen, and welcome to another EPICentre seminar and discussions. Today we have Professor Ian Robertson, who is going to talk about status of tsunami design in earthquake in the USA. I was just checking whether I'm mute or unmute, sorry. So Professor Robertson is the Professor of Structural Engineering and Chair of the Department of Civil and Environmental Engineering at University of Hawaii in Manoa. He's a registered structural engineer in the state of Hawaii and is the past president of the Structural Engineering Association of Hawaii and the past chair of Hawaii State Earthquake and Tsunami Advisory Committee. His research interests include the performance of steel and concrete structures during seismic, hurricane, tsunami, and other extreme loading events, the long-term behavior of reinforced and pre-stressed concrete structures, material properties of bamboo, coconut, and other tropical timber, and the corrosion of reinforcing steel and galvanized light gauge steels. So Professor Ian Robertson, thank you very much again for sharing your research with us. The floor is all yours. I will stop my sharing and we'll wait for you to share.
All right, thanks, Siraj. Thanks for that introduction. I think you can see the first slide now. Am I right?
Yes, I can hear you and I can see the screen perfectly.
All right, great. I do want to recognize the professorship, Arthur N.L. Chiu, Distinguished Professor position that I hold, because that's what's funding my trip here to the UK. And so I like to acknowledge them. Arthur Chiu was an amazing faculty member at the University of Hawaii who focused on wind. We have hurricane threat in Hawaii. And so his mission in life was to make sure that we improved our wind maps for the islands. And it eventually happened, but unfortunately after his death, so he didn't see it, but he was the impetus for it. Let me see, I got to get this to advance. All right, so I might have too many slides. I always do have too many slides, so it might be like a fire hose. And some of you might have seen some of these slides before if you've seen a previous presentation of mine. But it's difficult to talk about tsunami design without looking at some of the history. So the Tohoku tsunami, I'll show you some of the lessons we've learned. And then how we developed the ASCE 7, which is our loading requirements in the US, a new chapter on tsunami design, and then touch on work that I've done with your colleagues here at UCL, particularly Marco Baguera on pushover analysis, and then some US buildings that have already used this design approach to build tsunami resistant buildings. As we go through, I'll highlight some of the changes that have been made in this new version of ASCE 7, published just a month ago, ASCE 7 for 22. So tsunami, obviously you're aware of the earthquake risk around the Pacific Basin, and Hawaii is right here. So a lot of these are aiming at us. And so we're concerned about what might happen when we see a large earthquake around the perimeter of the Pacific Basin. And Japan, of course, had the Tohoku tsunami, or the Great East Japan earthquake, which resulted in major inundation along the northeast coast of Honshu Island. And at the same scale, we have a subduction zone right off the coast of Washington, Oregon, Northern California, which threatens similar population along that coastline. So it's of major interest to the US. And this is the ocean wave amplitudes from that Tohoku event. And you see Hawaii here, we had about $40 million worth of damage. Fortunately, no lives lost because we have warning systems. But it was a major event, as you know. And so we managed to visit after that event, and the Japanese have prepared well for tsunamis. So they have evacuation routes. They have signs on buildings and tell people to go up above the 4th floor. And indeed, this building survived inundation to about the 3rd floor, and everybody in the building survived. Here's an example of a school building, elementary school, where all the students got up onto the roof, which was designated for vertical evacuation, and they survived. Some of the lessons they learned was that after the first inundation, they all came down. They thought it was over. And then the water started coming back again. So they all scampered up. They did this 3 times, down and up and down. And eventually realized, well, we better just stay on the top until somebody tells us it's over. So there are lessons to learn. Some of the big lessons that we learned were from places like this, Minami Sanriku. This is a large inundation area. And a number of interesting locations. You can see, first of all, they had a seawall all the way along the coastline that has since disappeared. So the tsunami was substantially bigger than what they planned for. However, they had the sense to move these institutes onto the high ground. And those were the elementary, the middle, and the high school. So they've learned from history that if you want your children to be safe, you keep them outside of the inundation zone. Not cheap, it's expensive, but it's good that they did it. And the community knows where the schools are. You drive your kids, your grandkids to school. So everybody knew where these were, and they become ideal evacuation sites for the valley. But around the turn of the century, they built a sports field right on the coast, and were worried about the number of people who might be there when there's a tsunami. So right next to it, they build a residential 4-story apartment building, city-owned, as a vertical evacuation structure. And I'll show you that in a minute. Also in the inundation zone was the Emergency Operations Center and a hospital. So this is the building right on the coastline, 4-story residential structure, 99.9% of the time. It's just a regular residential building, but the roof has elevator and staircase that go right to the roof, which is unusual. And then a very substantial barrier around the edge of the roof. And you'll notice some debris on the roof because the water went over the top of this building. This was an extreme event for the water to get that high. But the 44 people on the roof managed to survive. They got wet and it was cold. Remember, this is winter, March 11th. You see some of the videos and there's snowflakes falling. I mean, it was just miserable. And they stayed up there the rest of the night because they didn't want to go down. The waves were still coming in and out. So it's a frightening experience. The reason the building survived, of course, was because it was built to a tsunami standard in Japan, which is a very conservative standard. You can see the amount of scour. This is where the dirt used to be. And now the scour is below the bottom of these pile caps. You see it here. But fortunately, they used deep foundations, piled foundations, and so the building survived. So we can obviously build for tsunami. The Emergency Operations Center was also designed for tsunami. It's a moment frame, structural steel moment frame building, and the roof was their evacuation site. The mayor and 29 of their emergency workers responded to this building after the earthquake, and they were reading out warnings over the loudspeaker system for people to evacuate. Only 24 of them made it to the roof in time. The others perished while still calling out the warning. But unfortunately, the building wasn't tall enough. And so in the end, only 9 people survived. The mayor was one of them, clinging to the handrail on the staircase, which turned out to be stronger than the handrail around the rest of the building, the rest of the roof. So you've lost 21 of your prime emergency responders in one event. It's dreadful. These are mistakes we cannot make again. You'll see a hospital. This is the hospital in the background, right? Water coming out of the top floor of the hospital. Fortunately, there was a wing next door with an additional floor, and they moved most of the patients over, but there was still a lot of deaths in that hospital. So keeping the hospitals, the emergency facilities out of the evacuation or the tsunami zone is important. So some of the biggest lessons we learned was that historical records are not enough to guide our future. In fact, the one thing we know about history is it actually doesn't repeat. When you're talking about natural hazards, earthquakes, tsunamis, hurricanes, the same event will never occur again. It'll always be different. And unfortunately, the Japanese were using their 1,000+ years of record as an estimate of what was going to happen in the future. We need to do better. We need to use a probabilistic approach and look at the worst possible conditions and decide which of those we want to design for. So that's what we do in this ASCE 7 guidance. So looking at ASCE 7 itself and the scope of that chapter, first of all, ASCE 710, ASCE 7 is the Bible for structural engineers in the US. It tells you all of the loads, gravity loads, wind loads, earthquake, rain, snow, everything except tsunami. So this was the catalog of chapters in that ASCE 7 back in 2010. And chapter 6 was empty because it used to be the wind load chapter, and they decided to move it to multiple chapters at the end of the book. And so we filled that in the ASCE 7 2016 version with this Tsunami Loads and Effects chapter. Unfortunately, the book's getting very big. I have a 1988 copy of this book, and it's about 1/4 of an inch thick. Now it's 2 manuals. One of them is the provisions on the left, which is the actual code language, and on the right is the commentary, which unfortunately now people probably won't read because it's sitting on the shelf collecting dust. But the commentary is actually very important for you to understand what the legal language is actually telling you to do. This is referenced in turn by what we call, euphemistically, the International Building Code, which nobody uses except the US. So there's nothing international about it, but that's its name. So the 2018 version of the US code references ASCE 716. And since then, there's been an IBC 2021, and they're now working on IBC 2024, which will reference ASCE 722, which is the new version of ASCE 7. So that's the progression of the codes in the US. The provisions for tsunami design only strictly apply to what are called risk category 3 and 4. These are large occupancy, critical and essential facilities. But we try to encourage local jurisdictions, cities, counties, states, to adopt tsunami design for taller risk category 2 buildings, which are residential, office buildings, apartments, hotels, because people are going to use them like they did in Japan to evacuate vertically. And we should at least be cognizant of the tsunami loads on those buildings and make sure they're going to survive. So the chapter 6 is based roughly on the content of this dashed rectangle. This was actually work that I put together for a proposal to NSF back in 2005, which eventually got funded and initiated the research that led to this chapter 6 development. But we already knew that the USGS had done a lot of work on where these tsunamis come from, on understanding the earthquake sources that we don't need to reinvent. There was a lot of open ocean propagation that was already, tsunami modelers were performing ocean propagation. But the things that were lacking were accurate inundation modeling, the flow velocities as the water comes on land. So this area we wanted to look at. At the other extreme, the consequences and the warning systems were already well understood after the 2004 Indian Ocean tsunami. And we already had warning systems in Hawaii for a long time. But what wasn't defined is how do we want our buildings to behave? What is the risk or the performance of our various risk category buildings? And to make that connection, if I know what the flow on land is going to be, the depth and the velocity, and I know what performance I need from our building, then we need the in-between understanding of fluid structure interaction, scour, structural response, erosion, etc. And so this is what our team worked on for about 5 years and developed this chapter, which runs through all of those items. Obviously, I'm not going to go through them all, but we introduced some of the basic requirements for tsunami design in the US. First thing is it's only required for what we call the 5 western states that border the Pacific Ocean. Because even though there is a hazard on the eastern seaboard of the US from possibly, hell, it might be Palma, right? That volcanic activity might eventually cause a landslide that causes a tsunami. But that risk is ill-defined. The return period of tsunami on the east coast of the US is somewhat remote. Whereas in the Pacific, we understand the return periods. We designed then for a 2% exceedance in 50 years. So 2% probability of exceedance in 50 years, which is equivalent to a 2,500-year tsunami, which sounds extreme, but that's also what we do for earthquakes. So we're designing on the west coast of the US for the Cascadia subduction zone, 2,500-year return period earthquake. That's also going to be the earthquake that causes your 2,500-year tsunami. So we better be consistent. And the hazard is mapped as a tsunami design zone in all of those 5 states. And I'll talk about that a little more. So looking at those risk categories, I mentioned risk category 3 and 4, tsunami design is required. So these are the categories of buildings, you see them written in here, that affect 3 in the hundreds to thousands or more than thousands of people. The hospitals, the emergency management, all of this critical infrastructure has to be designed. If it's in the tsunami zone, it has to be designed for tsunami loads. What we're trying to encourage, and unfortunately we've only succeeded in Hawaii, is to require tsunami design for office buildings, condominiums, hotels, the vast majority of our buildings that are tall enough to serve as vertical evacuation refuge. There's no point designing a 2-story building for tsunami if the water is going to go over the roof, because people are going to think that's a safe place to go when it's not. But if you've ever seen pictures of Waikiki, you'll see that there are hundreds of buildings that are multi-story, 10, 20-story. And those should be designed for tsunami because people are going to use them. We tell people to use them for vertical evacuation. So one of the projects I've been working on recently, which has been incorporated into ASCE 722, the current version of ASCE 7, is probabilistic mapping of tsunami hazard in Hawaii, which gives us ultimately the flow depth and velocity, and therefore the tools we need to design structures anywhere in the tsunami zone. And this was funded by NOAA, funding from NOAA through our coastal zone management program. And the folk I worked with, I'm not a modeler, but I know something about tsunamis, so I was able to manage the project. The people doing the modeling are Yong Wei of PMEL and the University of Washington, and Kwok Fai Chung, who I think is one of the best in the world at tsunami modeling. He's at the University of Hawaii. And we had an independent technical peer reviewer, if you like, Patrick Lynette, who's another excellent, one of the world's best tsunami modelers. So the reason for repeating this mapping, ASCE 716 already has tsunami design zones mapped, but they were mapped at 60-meter or 90-meter resolution, meaning the integration points were 60 meters apart. You could miss an entire freeway embankment. You could have a road going through there that blocks the flow, but you'd miss it if you're only monitoring every 60-meter points. So it was a very low resolution mapping. It was that way because of the finances. There wasn't enough money at the time to do a better job. And the hope was that each of the states would incrementally do this themselves. And so we have now moved to a 10-meter resolution. And now almost everything gets picked up. All of these things, berms, levees, elevated roadways, river channels, fringing reefs, channels in the reefs. It's a far more detailed digital elevation model and numerical modeling tsunami study. The problem is you've gone from 4 integration points to what, 36. I mean, the amount of time it takes to run the model is going to be enormous. And in fact, the model that Fai Chung developed takes about a month to run one tsunami scenario, 3 weeks to a month. So the need obviously is because the original maps were developed with low resolution. We miss some areas that are going to be flooded. And sometimes we think areas are going to be flooded that actually don't get flooded. And so you're building for tsunami where you don't need to, and you're missing it in other areas. So it is important to improve the quality of these maps. California has already done it for all of their highly populated areas. And so it was good that we could get the funding to repeat that effort. All of this information is going to go up onto this hazard tool, ASCE Tsunami Hazard Tool. That's the current website. And they're adding the 2022 maps now. So I don't think they're live yet. This is the older ASCE 716 map. But they're very useful maps. They give you the wave height or amplitude around the 100-meter bathymetric line. So where the ocean is exactly 100 meters depth, we give you the wave amplitude for that 2,500-year event. Because that is the compilation of thousands of tsunamis from around the Pacific Rim. So that when you're running a site-specific analysis for your particular building, you only have to run one, maybe two scenarios from the Aleutians and Kuril-Kamchatka, for example, but then you have to match them to these offshore wave amplitudes before you allow them to run onshore. That way we can ensure that you're consistent with this 2,500-year event. And then the orange triangles show you the run-up elevation, how high on the land the wave will reach, or the water will reach. Another nice tool from this probabilistic analysis is that you can disaggregate the source. You can find out where the governing tsunami waves come from. And for us in Hawaii, so you see the red dot down here in Hawaii, the main source is the Central Aleutian Islands and Kuril-Kamchatka. Fortunately, these ones are blocked by some mid-ocean. They're not islands, they're actually slightly below the surface, but that's enough to interrupt and disperse some of the tsunami activity. But the energy coming from the central Aleutians is what threatens us the most. So here's the digital elevation model that Fai Chung has assembled over many years of tsunami modeling. It's based now on LiDAR data, so it's extremely detailed. And the model that he uses is known as NeoWave. The traditional models are hydrostatic. They assume that the water does not move up and down, it only moves horizontally. That takes away a whole 1 degree of freedom for every one of these analysis points. Fai doesn't believe that's the right way to do it, because water does move up, especially when you're hitting an island which has a very steep bathymetry. The water definitely moves up. And so he felt it was wrong to ignore that. So he added that third dimension and calls it non-hydrostatic evolution of ocean waves. That also leads to more realistic dispersion. The wave separates more realistically as it does in reality. He also captures the bore when the wave gets steep enough, it breaks, and he captures that shock energy in his model. And he also models two-way data transfer, not just from the source, from the larger low resolution modeling to higher resolution as you get closer to shore. His model works both ways. So it's considered a higher order tsunami model. So when you're modeling tsunami coming from the Aleutians all the way to Hawaii, you start with a very coarse grid covering the entire Northern Pacific. That's level 1. And then level 2 grid is more fine, 720 meter integration points, and covers all of the islands, brings the waves to your island, which is then modeled at a closer grid of 90 meters. And then each of these individual level 4 grids on each of the coastal areas is modeled at 9 meter resolution. So that's how you get the energy from the source all the way to your site, or for us, to the entire coastline of Oahu. So I've got a couple of videos. We'll see if they do run. Yeah, they will. So this is obviously sped up. You can see the time running in the bottom right. We're at 2.5 hours, 3 hours. Let me just pause it there. So it's about 4 hours warning that we have after an earthquake happens in the Aleutians before it gets to us. So there is time for evacuation, but not for a place like Waikiki, where there are 200 to 250,000 people in the hotels and the residences. They're never going to get out of Waikiki in time, which is why we tell them to go vertically in those buildings. So that runs through the islands. You can see all the reflection and dispersion of the waves. This is looking now at the islands, and we're starting at about 3.5 hours as the wave comes down from the north. And we're mapping Oahu. At the moment, we're working on Maui and Kauai as the final phase of this project. But we've just completed Oahu. And you'll notice, sorry, if you don't keep these live, then they go away. Let me go back. So you'll notice how the waves wrap around the island, but not only that, they bounce between the islands. So just keep an eye on, let me pause it there. Keep an eye on this spot here. There's a lot of very shallow, less than 100 meter bathymetric areas between the islands. And those tend to trap this energy. They start to resonate with the incoming wave. And so long after the wave has gone through, they will still be vibrating. And so you'll see this chunk here and this chunk on what's called the Penguin Bank. And you notice it bouncing back from there to the south coast of Oahu. That is the worst effect. It's not the wraparound. It's actually this reflection and this resonance within the islands. And for hours afterwards, we're at 6.5, pushing 8 hours. So the tsunami's been and gone, but there's still enormous waves traveling around. There's big inundation happening in Ma'alai. So yeah, do not think the earthquakes, the tsunami's over after the first wave. It could go on forever, or at least for another 8 hours. And then looking at the island itself, you'll see this reflection coming to the south shore. Very big inundation on the north shore, obviously, because that's the direct hit. The south looks like it's not going to get anything until we get this bounce back from Molokai coming across the channel. And you'll see that right here. That's actually one of the worst reflections coming back. So it's a tricky thing to understand what's going to happen to your community. So this is Waikiki right there, getting completely submerged. The house I used to live in is up on this hill, so it's out of the way, fortunately. But some of these reflections are actually the bigger portion, not the first wave, but here the second, third wave. And they're not really waves, they're more the resonance between the islands. This is our port, so a lot of damage in the port. This is our airport runway. We're not going to be flying in and out for a while afterwards. And the last one is velocity. And the interesting thing with velocity, I'll stop it right there, is the wave comes in fairly uniformly across the entire coastline. So there is some scour during the incoming flow. But you'll see when you watch the outgoing flow that the scour is much more significant because the current now focuses, once the waters come in, the drawdown is as if you have a dam break. The ocean has receded, and now all of that water has to run downhill and get back to the ocean. And it's as if you had a flood. And it's a hydrologic study now, studying where the water will go. And it's going to go through the channels, the existing channels. And so we get enormous scour happening in these existing, it may make some new channels of its own. You'll also notice the turbulence, the eddies that form as the water comes out of these channels. Phi's model is very good at capturing that eddy effect, which we see in past tsunamis. So some of the products we provide for the state are the flow depth, how deep the water is going to be, the flow velocity, speed. I should say speed, it's not velocity. We do give the north, south, east, west velocities, but this is the maximum resultant of those velocities. And then the product HU squared, or the depth times the velocity squared, which is the momentum flux, which is proportional to the loading on structures. And you'll notice again, this is Waikiki, this area right here. And they get some of the larger loads. The airport runway, forget about it. There are no buildings there, obviously. But the Waikiki, these buildings need to be designed for tsunami. If we're going to tell people to go up in those buildings, we would best be designing them. And so we provide these maps all the way around the island. And it's substantial. This is a major event. If we get a Tohoku-sized tsunami in Hawaii, it's going to be a mess. I show you this one on the Kailua side because I've just moved from Oahu, from Manoa, where the university is, across to the other side of the island, because my son and his wife bought a house right there out of the tsunami zone, thank goodness, and had our grandchild, first grandchild. So we decided we needed to be closer to them. So we bought a house now in Maunawili, and I also made sure we were outside of the tsunami zone. I know that much. So the ASCE 716 has this geodatabase that I showed you earlier. And when you zoom in on it, you can cut transects through the inundation zone. It'll give you the topography based on the digital elevation model. It'll give you it as a table. And you can extract that and then run what we call the energy gray line analysis. This is a relatively crude but simple approach of working back from the run-up to determine approximate flow depth and velocity at your site. We created it because not everybody wants to spend the money to do a site-specific probabilistic analysis. This would be synonymous with doing a seismic geotech analysis, right? A site-specific geotech study. Whereas this would be just looking at the maps and pulling off the values for ground shaking. This probabilistic could also be thought of as a wind tunnel study for wind. You can use the code prescribed wind loads, pressures, or you could do a wind tunnel test and get more accurate values of what you expect. So not everybody wants to spend that money. So we developed this grade line analysis to solve that problem. And when you apply it to a location like this is a building in Hilo on the Big Island, we do require that you run not just the perpendicular transect, perpendicular to the shoreline, but also 22.5 degrees either direction, because the flow doesn't know that we want it to come in perpendicular. So we need to consider some variability. And you get the depth from the run-up point all the way down to the shoreline. So at your building, you can find what the flow depth is going to be and the flow velocity. And you pick the worst of these three transects and you use those values for your design of your building. A colleague of mine, Ron Riggs, wrote a software program to do that analysis. I was thinking of it as one of the things we could put on your, Jonas is working on developing a web portal with all of the tools for, but Ron sells his program, but he sells it for $99. $99. I mean, I told him, you're not going to make any money. He says, well, I don't need to make the money, but it's like charge 500 and people think it'd be worth having. But it really is worth having because it makes this so simple, the energy grade line analysis. So if you're interested, it's available. I've got the website down there and I'll leave these slides with Tiziana so that she can distribute them to folk. All right, so getting into the design itself, we now know what the hazard is. We know the flow depth and the velocity, but we only know the maximum flow depth, which is there, H max, and the maximum velocity. That's what we get out of the energy grade line analysis. So we developed these normalized time histories, which are based crudely on some video evidence from Tohoku tsunami. But again, if you do a site-specific analysis, you're going to get the exact time history of the tsunami, or at least a better one than this crude value. And the velocity, which increases to a maximum, we believe at about 2/3 of the maximum flow depth, but that's not gospel. It's going to vary from location to location. But we had to develop something like this so that the engineer could use these load cases at the maximum velocity and at the maximum depth to verify that the building is adequate. And then we consider all of the loads: buoyancy, buildings floating, hydrostatic, hydrodynamic loads, the effect of debris damming on the face of a building, like this one that was damaged because of the amount of debris. And we present all of these loads: hydrostatic loads, hydrodynamic loads, drag, tsunami bores on a wall, stagnation pressure, shock pressure in entrapped bores, something going underneath a wharf or a harbor pier and hitting the bulkhead at the back and being trapped produces enormous pressures, uplift pressures. And then waterborne debris, impact from cars, poles, shipping containers, large ships, extreme events, etc. All of these are covered, including scour effects and how you can try to remediate the soils to minimize the scour. So all of this is included. I'm not going to cover many at all, except ones that have benefited from work done here at UCL. So on the buoyancy uplift, obviously buildings have been seen to float, not just light framed timber buildings, but concrete buildings. During Tohoku tsunami, they floated all over the place. One of the ways to avoid that floating is if this is the hydrostatic pressure that's going to develop down the side of a building until the breakaway wall or the glazing fail. And so we assume that that doesn't happen until the water gets to the top of the first floor windows, the ground floor windows. And at the same time, that pressure is going to develop underneath the building, depending on the type of soil. Sandy, gravelly soil will assume the same pressure as the hydrostatic pressure at the side of the building. The way to avoid that is that you make your ground floor slab non-structural. If it is not capable of transferring that pressure to the frame, it's not going to lift the building. And so isolating your slab from the frame, the pile caps, grade beams, and the columns means that that slab will simply fail and you won't float the building. Easiest way to solve the problem. Trouble is then you've got these big tumbling mass of slab on grade roaming through your building, impacting the columns. And we hadn't thought of this in the ASCE 716 version. So we've now added a requirement. If you use these breakaway slab on grade, then you have to design the interior columns for this tumbling debris. So that's something we've added now. Because of the work that Marta, one of your colleagues working with Tiziana, Marca De Zoppo, has worked on the effect of buoyancy because of air trapped below the floor and the air above the floor until the framing on the second floor, the exterior wall, until it fails, there's no water on that floor. And so there's actually quite an enormous amount of buoyancy that can develop. And that lifts the building, which reduces the axial force in these columns. And if they're concrete columns, that generally will reduce their moment capacity. So it's we added a section in the commentary to warn the engineer that they need to consider this effect. They can't assume full gravity load during the tsunami. Not just submergence of your structural elements, but these buoyancy effects because of the trapped air or the open spaces on upper floors. And we saw that during Hurricane Katrina, which was way back in 2005, where buildings like this with double T, precast double T, pre-stressed planks, spanning multiple 60, 70 feet in some cases, but with bulkheads at the end that trap the air. So as the water comes up, there's nowhere for that air to go. And so these basically float and break backwards, right? Pre-stressed sections are already stressed to counteract the dead load. Now you're putting buoyancy underneath them, and basically the first elevated floor of 10, we found 10 of these parking garages that had completely failed. The second floor used to be up there, now it's down on the ground. So buoyancy is real. Ask Archimedes. He knew about that. Another area that we benefited a lot from work here at UCL, and I know you will have seen these slides, many of you will have seen them from Marco himself in presentations that he's made, so I'm not going to show them all. But one of the options that we give the structural engineer is, as you're designing your lateral frame system and your structural components, the columns, the beams, the walls for tsunami load, you can use our prescriptive approach, strength design, prescriptive loading, etc. Or you can use a performance-based. And we allow you to use linear and nonlinear static analysis, which means pushover type analysis. But we don't tell you how. And the only pushover analysis that people are familiar with is seismic, which is actually not a good application of pushover, because seismic is a highly dynamic, and a pushover is a monotonic loading on the building, slowly increasing the load, pushing it over. That's not appropriate for an earthquake at all. But it is appropriate for a tsunami, because that's exactly what the tsunami does. It slowly increases the load on the side of the building and tries to push it over. So I actually prefer pushover analysis for tsunamis than for seismic. Anyway, and so you might already have heard of constant depth pushover and variable depth pushover, both of which were developed here at UCL. You can see some of the researchers down below. The disadvantages with these is the flow is not constant depth. A tsunami doesn't start at 3 meter deep and simply accelerate. It starts at 0 and grows while it accelerates. So that's why the variable depth was introduced. However, the problem with this one is it assumes a constant Froude number, which also isn't strictly true. And so what Marco did was to incorporate a two-phase variable depth pushover, but geared specifically to following those time histories that I showed you earlier for the flow depth and the velocity that we think represent better the change in depth and velocity based on the Tohoku tsunami. The two-phase is that he starts out under load control, and then as soon as he reaches instability in the model, basically meaning that the structure is starting to fail or some components are failing, he switches to a response controlled or a displacement control analysis. So it did a very good job developing that. Then applied it to a building that we had already designed prescriptively. So I had the students down below designing this following ASCE 716 prescriptive design. And Marco took that building in Seaside, Oregon, and basically applied the pushover analysis. He did that using OpenSea's extremely powerful analysis program, nonlinear analysis program that uses a fiber model, so a highly detailed representation of the material in the column, for example, but as a two-dimensional model. So he had to take this three-dimensional building and break it up into a series of frames to mimic all of the response of all of the components. Quite a tedious task. Not something that the design engineers will do, certainly in the US. They don't have the time for that. But one other thing, though, that Marco did in the process was he had to digitize what we had drawn just as a replica of video evidence from the Tohoku tsunami. So he developed these equations for best fit equations for these depth and velocity time histories, because he needed to follow those as the flow depth increases and the velocity increases through the tsunami. And he came up eventually with the pushover analysis that looks like this, very similar to a seismic pushover, which is down here, but it looks like it's a lot more stiff. That's because the load is applied at the bottom of the building, whereas in seismic, most of the load is applied higher up in the building where the accelerations are large. So it's a very different response. But this dashed line represents the maximum load during that tsunami affecting yes, by all means. This is the maximum load expected at that location of the building in Seaside, Oregon. And so he was able to show that the pushover analysis gives us significantly more strength than that load. Whereas when we did the prescriptive design, we actually had to increase the strength of the building to get it to work. So doing the nonlinear pushover analysis can save you significant money in the design or retrofit of a building. So this has just been published. I think it was finally published last month, or maybe even, yeah, November, after a lot of effort. But yeah, very good publication. So that has gone into ASCE 722. We now use Marco's paper and his guidance to guide the engineer on how to do this pushover analysis following ASCE 7 assumed flow parameters. So that's a very good improvement to what the engineers have. And we included figures that were based on what Marco put into that paper, showing you how you apply the loads either at the floor levels or distributed up the column. He showed that the difference is minimal. And so you can do either of those two. For the overall systemic or structural system for the building and for individual components, each individual column has to be analyzed for increased loads on that column. Think of wind loading. When you're designing a single window, you use a higher pressure than you do for the entire building, because for the whole building, you're averaging the pressure. It's the same with tsunami. The force on the entire building doesn't mimic the possible force on each individual element. So to protect these individual elements, to design them appropriately, you have to put the increased load on that element and then reduce the rest of the system load on the other elements and analyze the full building again, and do that for each of the individual components that could be critical to the performance. So this is now explained in ASCE 722 appendix. I now have a student, Derek Argater, who is working on a simpler model. So OpenSeas, as I mentioned, is a very complex model. It's not used by design professionals much at all, more by researchers. ETABS is used by almost all of the structural engineers in the US, or something similar. Strudel, STAD, RISA, all very similar programs. If they have a nonlinear component, then it is a lumped plasticity. It'll be at the end of the column or the end of the beam where we assume the yielding is going to happen. It's not a distributed fiber model. So that's a disadvantage, but it's so much simpler. and engineers are familiar with it. It's easier to put together a 3D model, saves the trouble of splitting it into 2D. You have to predefine the yielding behavior of those lumped plasticity points, whereas in the OpenSea's model, you define the material constitutive relationships. How's the concrete going to behave in compression, in tension? How's the steel going to behave? Because each of your fibers consists of one of these materials. One of the advantages with the ETABS is that it does both a flexural bending check on your members as well as a shear check, whereas Marco had to do the shear check as a post-processing to check if there was a shear failure. Another advantage of ETABS, of course, it's a commercial program, and so they create these nice graphics that you can see how the building's behaving. You can see which joints fail first. You can see what the building looks like. You can see that this is a tsunami analysis because it's only the bottom of the building that's moving. The top is just moving laterally, but it's not deforming. So you get a better user interface with a program like ETABS. But the result ends up being very similar. So Marco's analysis of this identical building, we used exactly the same structure, structural properties, etc. Marco's is the gray line, running slightly higher, which you would expect because the fiber model will give you benefit of the distributed plasticity rather than lumped. The lumped plasticity with ETABS seems to be a little stiffer, but that's simply because the areas where you've lumped the plasticity will take longer to develop or to reach whatever you've defined as the yielding capacity. Whereas the fiber models are yielding right from early on. You're getting cracking in the concrete, you're getting yielding of the reinforcing, etc. So it's a much more precise model. But the result is remarkably similar. And this, I'm hoping I can work with Marco to publish this work and Derek, because I think this is going to be very encouraging for engineers who want to use nonlinear analysis for tsunami design. Finally, one other update on the ASCE 722. Let me check my timing. Ooh, I'm going way long. Well, the reason I tell you this one is if you're doing research on loading on components, this was pipes. We don't cover pipes at all at the moment. But Iwan Nista, University of Ottawa, did a whole lot of research. You can see the thousands of tests on various sizes, shapes, and elevations of pipes and developed expressions for the resistance factor and the uplift factors. If you're doing research on tsunami loading, we would love to hear the results because these have now been included into ASCE 722. So finally, a little promo for my book. If you want to learn more about tsunami design, by all means, just give me a call. I got a couple of spare copies. Otherwise, you can buy it from ASCE 7, from ASCE. I want to show you two buildings that have used this chapter to design for tsunami evacuation. One is a school building on the top, and the other one is a university campus, both on the coast. The school building is on a peninsula that's going to be totally overwashed. So the water is going to go right over the top. The school is right there. And this is the existing school, and they were going to be expanding, adding classrooms, and adding an auditorium, gymnasium for basketball, etc. And so they decided that they would improve the strength of the roof, add 4 staircases to get people to the top of the roof, and use those as the shear walls to brace the overall building. They would protect the steel columns by encasing them in concrete for debris impact, and then the roof becomes the evacuation zone. So it cost another $2 million to upgrade the building to that status. But if you work it out, it's only pennies per day for each child who's in the school. And that buys peace of mind. The parents don't have to think what's going to happen when there's an earthquake. They know their children will be safe. So these are a great addition to that community. Oregon State University has a marine science center right down here on this peninsula in Newport, and they were building a new building, and they decided we should make that a vertical evacuation structure so that everybody on the campus can go there if they need to. And so there's a ramp that goes up to the roof. It's open 24 hours a day. There are no gates, no locks, nothing to keep people out. It's now complete. They started occupying it last fall. And it now gives peace of mind to everybody working in that community. So That's in a nutshell, not a nutshell, it's a big nutshell. I'm sorry, I've run way over my time, but I'd be happy to take any questions if there are. I see one chat. Let me just read that quickly. It says, is it different for tsunami design caused by earthquake and landslide? Example, Krakatoa volcano. Yes, indeed. Good question. What are the factors, design considerations, difference? The big difference is the hazard itself. An earthquake will cause a tsunami. Typically, the subduction type earthquakes that we're considering around the Pacific cause a tsunami that will travel across the ocean. A landslide would have to be an enormous landslide to do the same thing. So landslides have a very localized effect, such as that Krakatoa collapse, which killed, I think it was in the hundreds of people along the Sunda Strait between two of the Indonesian islands. The downside with that landslide was there was no earthquake. So there was no warning for people on the shoreline that something's going to happen. So it just happened. The water came in and washed them away. So that's the scary thing with a landslide generated tsunami. However, once the tsunami gets on land, it's water flowing with a velocity and a depth. And so if you know the landslide risks in your area, and for example, Alaska has this problem. They have a lot of very deep fjords, very steep mountainous fjords. And when there's an earthquake, there are always landslides. It just happen everywhere. If you know that there are landslide potential, then you need to estimate what the tsunami wave will be from those landslides. And it'll normally only affect communities in that same fjord. Once it gets out of the fjord, it dissipates and becomes much smaller. So yeah, that's the main difference between them. But once you have characterized the source, you can develop the flow depth and velocity at any site affected by that source. So the design will not change. The building doesn't know that the flow came from an earthquake or a landslide. One difference, though, to an extent, and we need to do more work on this, is that the earthquake may already have damaged your building. If you're close to that subduction zone, you feel a 9.0 earthquake, and then 30 minutes later, you feel a design level tsunami. How much damage is there in the building, and does that affect the tsunami resistance? That's something that I know I talked with Marco about working on, but he had enough on his plate. And Jonas, I see he's saying, no, don't talk to me about it. I got enough to do already. But it is in the pipeline. I think it's a good thing to look at. And some of your researchers here at UCL have already looked at the combination of those two. Time history analysis for the earthquake, followed by time history tsunami analysis. I think it's an important next step. At the moment, we assume that the building will still be structurally sound. If it's designed to ASCE 7 seismic provisions, it's going to be in pretty good shape, especially risk category 3-4 building. They're designed to a fairly high standard. Any other questions? Yes.
Yes, so I'll just thank you for a very interesting presentation.
I have one more
in the class.
question
Okay,
coming.
we can't hear. If you can repeat the question, that
I
will
will
be
repeat
perfect.
the question.
Thank
Yes,
you.
it's coming. Yeah, so the question is about strengthening existing buildings. The advantage of ASCE 7 is that, again, it's developing the loads on a structure. The tsunami doesn't know if it's a new building or an old building. The forces are going to be the same. And so we can use this kind of pushover analysis to assess the performance of that existing building, given the flow properties at that site. And then you can talk about using carbon wraps on the columns or whatever retrofit you want, adding structural walls, adding bracing to try to save the system. So yeah, it can definitely be used for retrofit of existing buildings as well. Yeah. Yes, so evacuation is still very important. We don't do any design for residential structures. You got a 1-story, 2-story building, forget about it. It's going to be gone. You just come back later and rebuild, but you need to evacuate. Yeah, but we want to give them options of evacuating vertically. So the more buildings, tall buildings that we can design for tsunami, the better. Then people have the option of going up in those buildings. Yeah. All right, and I've taken all of your time to 1 o'clock. Thanks very much.
Perfect. Don't worry if like people are still around. Feel free to ask your questions.
Sure.
The wave reflection and the bounce back was very interesting. I never thought about it. And then that causes evacuation problem as well, because people see the wave coming from the north, so you go to south while the actual one is coming from south.
South, yes.
I have a question regarding the code. Does the code suggest any opening size? Should we have big openings? Should we have small openings? I was looking at the CGI photos that you were showing, and there were openings at the bottom. So is it suggested or not?
Well, we do give some credit if you have what we refer to as an open structure. If you have the lower levels of your building are basically flow through, if you have breakaway walls that allow the water to go through predictably, then you reduce some of the loads. So yes, we do give credit for a building that is designed appropriately. And so I'm working with a local design engineer in Honolulu on 2 buildings in Waikiki, and they are putting the parking level at the first floor. So the first floor is 14 feet, what's that, 4 meters? 4 meters high, the first floor, up to the second floor. And that's the parking area. So it's completely open except for a elevator core, a staircase elevator to get you to the occupied levels. That's the approach to use. That will reduce the forces. We give you credit for that. So there are some benefits to designing smartly, yes.
Okay, so it's just the problem of contents, which again,
sure.
you want to save your building. So,
right.
So it is suggested to have openings.
Yes, the contents are going to be destroyed anyway, unless you have a critical. So now I'm also working on a project at our sewage plant. So sewage treatment, wastewater treatment is normally right at the coastline because we use gravity feed to take the sewage down to the plant. And then we put the effluent, once we've cleaned it, out into the ocean. But that makes your critical facility, the wastewater treatment plant, vulnerable to tsunami. So this was a new building that was going to be built. And so we looked at 3 options. One of them was you build it at ground level, but you seal it. And then you have to fight buoyancy. So you got to put piles that will act as tension piles and hold the thing down. But you can certainly seal the building. You just got to make sure you don't let it float. The next option was that we raise it on columns, and we use the bottom level for parking. Nice shaded parking, sounds wonderful. That gets more expensive because you're now elevating the building, the ground floor is becoming a structural floor, etc. The other option was to bring in enough fill that we could raise the grade by 12 feet, 3 meters, to get you above the tsunami flow at that location. That turned out to be the most expensive because bringing in fill is a lot of money. So yes, there are ways to solve the problem. Plus, that fill had to be protected against scour. So that added expense. So there are multiple ways of skinning a cat, as they say. There are multiple ways of solving the tsunami problem. But the earlier that the architect and the engineer get together and start talking about it, the better. These buildings in Waikiki had very narrow walls down in the bottom level, and they had to increase them. That screwed up the whole parking plan because parking spaces have to be a certain width. And if I made the wall 2 inches thicker, suddenly they contravene the parking rules. And so now the whole arrangement the whole configuration has to change. So it's better if we get talking with the architect right at the beginning before they set their framing system.
Thank
All right.
you.
Sorry, I'm running quite long here.
No worries. If there's no other question, I still have one more question.
Yeah, by all means,
your models, they were modeling inundation, depth, flow, speed, all of these. Were they considering the topography of the location, or is just the elevation of the ground?
No, it is the topography. It's a very detailed model of the topography, basically based on LiDAR scanning, aerial LiDAR that has been taken of the coastline and the shallow bathymetry. In Hawaii, our water is so clean that you can fly LiDAR over the coast and read as far as 40 feet below the water level. You can read the elevation of the ground. So yeah, they're very detailed digital elevation models, or topographic maps, if you like. You need that, otherwise the flow doesn't replicate what's actually going to happen.
That is impressive. So thank you again. Very interesting. I'll just share my screen for a second. So again, thank you very much for everyone attending today as well. So as you know, our next speaker will be talking about climate change and mental health, the current evidence, gaps, and ways forward. So I will see you next Tuesday, 14th of December. Thank you very much. The recording of this session will be available on EPICentre YouTube channel as well. So thank you.
Thanks, Arash. And thanks everybody for attending. Thanks.
Thank you.